Alright, so we have a finite talk for this morning, given by Hans. Please,
Thank you very much. This is joint work with Carla, Jesper, and Céline. All three are also participants of the workshop. Carla is here, and Jesper and Céline are online participants. And I'll also be a little bit storytelling instead of really mathematics telling, because it's actually the question one of the questions we answered comes back from something I worked on 30 years ago, 25 something, and we finally found an answer to a question we had at that time. But and it's about bandwidth. And yes, Saket already talked about bandwidth. And I'll tell a little bit more, and then I'll mention a number of complexity classes, and then problems which are complete for one of these, and I'll end with some conclusions at the end. But let's go back to the very early days of fixed parameter tractability, where Downey and fellows they introduced this class fixed parameter tractability and W1 and W2, and I hope you are all familiar with these. There's this whole hierarchy of complexity classes, and then we know for some problems that there are complete for some of them. So independent set is complete for W1, and dominating set is complete for W2, and I'm still one of these people who are actually interested in whether it's W1 or W2 or maybe somewhere else in this hierarchy. And I think this is also what we asked. And so basically, if you want to define this, the best way of thinking about this is you take satisfiability. The number between the brackets is more or less the depth of the formula of the number of times that n's and or's are alternating. This is vaguely, and then I want to know whether I can make this formula true by setting k variables to true and the rest to false. So that's basically Wi. So I is alternations between n's and or's in your formula. That's the intuition there. So bandwidth. So bandwidth, I have this graph, and I want to number the graphs, the vertices from 1 to n. And then I'm such that for every edge, the difference between the numbers is at most this number k, the bandwidth. And it's a classic problem. It's basically one of the reasons people studied this already many years ago, because it's basically the question: I have a symmetric matrix and I want to reorder the rows and columns such that all the non-zero elements are at a band around the main diagonal. And that's useful for Gaussian elimination, and that's why people, I think, studied this even before I was born already. It's shown to be NP-complete even for very simple types of trees, caterpillars, which is basically you take a path and you attach some path to the path. And then in 1994, my fellows, Mike Hallett and I wrote a paper. That was still the time that you could actually publish papers in conference proceedings without having written down the entire proof. And I had this proof in my head about the fact that bandwidth was WT hard for all integers t for trees. And I started writing it down, and then I was busy, and it was very complicated. And I forgot, and then people reminded me, Hans, Mike came to me, Hans, you should write down this proof, you promised this to me. And so I was, and then in 2014, at least Daniel Laxdorff and Regi, they showed wrote down actually that it's W1 hard for trees, and they gave a very nice ETH-based lower bound. But then I was basically locked up in my attic in the summer of 2020 for obvious reasons, and I finally used this time to write down this proof. So you see sometimes, so there's a Dutch saying that every disadvantage has its advantage, by a famous soccer player, and that was one of the things of this summer. And also, but what we know now, so there is still one question which was not answered, because in 1994 we thought, okay, it's WT hard for all integers t, but is it actually WP hard, or is it member of WP? Where is what's actually, we don't want to know hardness, we want to know completeness. For which class it's complete. And then Mike Hallett has an argument already in 1994 that bandwidth is not in this W hierarchy, it's not in WP. And the basic reason is that you can think about it as the certificate size of a solution. So like the definition of NP, I mean, if I have a certificate that of a satisfiability problem where I can set k variables to true, I need basically k log n bits, because for every true variable I need log n bits. But for showing that a graph has small bandwidth, you basically need something like n log k bits, because you need something for every vertex. So something at least linear order n less than n bits, that seems really strange. I mean, you could have lots of connected components and you need something for every connected component. So you need more space for a certificate than for a certificate for this weighted satisfiability variant of the W hierarchy. So that's the reason we don't have a proof, but we believe it's not there. But where is it? So, let's see. So then we go to basically the insights. Where it is actually, it's complete for this class, which we call XNLP, and it's if you go to classic complexity theory, there is this class called L, which are problems you can solve with in a deterministic algorithm with log n space. Then there is NL, which is basically a non-deterministic algorithm. And of course, these are subclasses of P, because you could just try all possible space configurations. But you can make parameterized variants of it, where you say basically, I don't use log n space, but a function of your parameter times log n space. And then one class which is not studied a lot, there was one paper by Elberfeld et al. In 2015, where they used this, where we do two things at the same time. So we use this logarithm, a function of parameter logarithmic space, and we use FPT time. So a function of parameter times polynomial time. So it's it's non-deterministic. That's the class we are looking at. And now the interesting thing is that bandwidth is actually in this class. And you use, to show hardness, you use a certain type of reductions. Let's skip that. Basically your reductions also need to use log space. So in 2015, Elberfeld looked at this class, which they actually call differently, but I think we like to use XNLP because it's nice to have an acronym with at most 4 characters. And they showed, for instance, that non-deterministic Turing machine acceptance with k cells, running time bounded by a polynomial, and is XNLP-complete. And then program cellular automata, and it worked very nicely. The longest common substance, which is really classic combinatorial question. And then what we did is basically we showed that there are really a lot of problems which all are complete for this class XNLP. So for bandwidth, why is it an XNLP? Well, there is a very old algorithm, like 1984 by Saxe, which shows basically that the problem is an XP, so this order n to the k plus 2. And what it does does dynamic programming. And what you can do is you can turn this into a non-deterministic algorithm by instead building the entire table, you always guess the next table entry and element. It's basically the classic way of going from a deterministic, non-deterministic to a deterministic algorithm is just to compute the power set of all possible states, but you could go the other way around and just guess a state. If you have a dynamic programming algorithm, you can make it non-deterministic by just guessing an element. And this gives actually basically, if you look at the algorithm, what happens there, it gives you precisely an XNLP membership, because what it does is it basically remembers the last k elements of your ordering, and then some little bit extra information. And k elements is just k vertices of your graph, which is k log elements. So, and then the algorithm guesses just the next vertex. So that shows membership, and then with a, so we have basically, you can see it's quite a sequence of reductions, where we start with this cellular automaton problem, then we go to a problem which people tell about that, a kind of a chained variant of satisfiability. We go over a problem of pathwidth, discovering on graphs about the pathwidth, chained multicolored click. One of my favorites is the accepted NNCCM. Then an intermediate problem, which I actually already mentioned, is in my thesis in 1986. So that's even earlier, right? And then we go to pathwidth. So, and at this last step, actually, that uses the proof I wrote down in the summer at the end. So that's this arrow. We can just copy of that. So what I want to do is just tell a little bit about some of the intermediate problems. And one of the things is actually that even, suppose I have this chain. Actually, for instance, we had to redo this tendons, but it's actually easier than the WT for all T proof. It's actually easier to prove XNLP completeness than prove something for T for all T's, because we don't have this alternation of ands and ors, which really alternating different difficult constructions in a hybrid proof, and you can actually, but hopefully I can sketch at least something there. So so the cellular automata, that was from Elberfeld. What you have is you have cellular automata, so we have basically an array. Every element of your array has a state, and every time step the state changes. You look to the state of your left neighbor and your right neighbor and your own state, and you get a new state. And it's like a game of life, but one-dimensional. And the question is that one state is called accepting, and then you say after t time steps, is it possible to have a run to come in an accepting state? And this is actually an example. They showed that this is XNLP-complete. And from that we go to weighted satisfiability, chained weighted satisfiability. So what I'm actually having here is, it's again a satisfiability question, but now where the formula is still in CNF. But my formula is a little bit of a chained form, because I have lots of sets of variables. From each of the sets of variables, I can choose k variables to be true, and all the others are false. But my formula just looks at it's just the big AND of something which is about the first and second set, and another part, second part of the formula goes about the second and third set, and so on. So the conditions are this on these pairs of sets. And yeah, so that's, and to prove that this is XNLP-complete, it's basically a reduction like Cook's proof, where you just write down in a Boolean formula, simulate the running of this cellular automata. So if you have seen the proof of Cook, then this is the proof here is no surprise. Yeah, and it's XNLP-complete. So So one of the other things which is really helpful for showing several of these hardness proofs is the acceptance by a very strange machine model, which I call the non-deterministic, non-decreasing counter-checking machine. But sometimes in my mind, one of these C's I replace by crazy because it's right. So what I have is I have K counters, and there are two types of things which can happen at the time step. Either I can be non-deterministically decide to increase a counter or increase all counters. And I can never increase them to more than n. So they start at 0, can never be larger than n. And then at some time steps, I decide to do a test, the next test from a sequence of tests, where every test is the following. I will take one counter, I have a value, and another counter, I have another value. I see if the first counter is the first value and the second counter is the second counter, then I stop and reject. And otherwise I continue, and if I just didn't stop and did all the checks, then I accept. So it's quite a simple model, but it's very useful to actually prove in hardness proofs for as an intermediate problem to show hardness. And it's again this problem question, is there an accepting run? That's actually XNLP-complete. So that's why
the checks, are they happening, sorry, but like do you have the same check that you run at every time step?
No, so there is a sequence of different checks. So basically, yeah, I mean the machine is basically described by the sequence. I mean, you have the number of counters, 0 and n. But the main thing is that I have this sequence of checks where every check is a for tuple. Counter 1, a counter name, a value, other counter, and another value. So I have this sequence of for tuples, and the question is, given the sequence of for tuples at n and k, is there an accepting run?
And these for tuples are all checks to be applied at every step.
No. So each for tuple is applied once in the sequence. Yeah, so what I do is I start at 0, I may do a random increase of counters, I do my first check, I can do a random increase of counters, I do my second check, and so on. And if I done the last check and it didn't stop, then I say yes.
Okay. It's about doing these checks in sequence and in between.
Yeah, so I do the checks in sequence, and in between I can decide to increase or not increase the counters.
Okay.
And yeah, so let me just use a few moments to sketch a proof for scheduling with precedence constraints. So this is really a classic problem from scheduling. It's open since I think a very long time. The question whether it's how hard this problem is if you have 3 machines. So I have a number of tasks. Every task uses one time step, and there is a directed acyclic graph where every task can only be done after the tasks which are before it in the graph are already done. And you can, of course, every machine can only execute one task at one time step. And now the question is, can I schedule this such that all the tasks are done before the deadline? And this is actually open since 1970, somewhere in the 1970s, open where how hard this problem is with 3 machines. And in 1995, my fellows and I wrote a paper where we show it actually, if you take as a parameter the number of machines, then this problem is W2 hard, so at least there is no FPT. And you can also show that you can actually take as a second parameter the width of the partial order, and actually if the width of the partial order and the number of machines are both parameters, then its problem is an XP with a quite straightforward dynamic program. But yeah, and so this is the notation in this class A. steady rotation. And what we now show is that if you take the number of machines n to its partial order as parameters, then the problem is actually XNLP-complete. So it's I hope people at home also see.
If you write to the right, they will see. But if you
so I think it's nicer to just draw a little bit on the board. So what I do is the following. I have a sequence of basically deadline number of tasks. So all these tasks, I mean, the person has to do a task number 1 and the task number 2. At some points when I do a check, what I can do is I can take lots of tasks which are all following directly the task from the time step before and are followed by the time step after. So there are lots of tasks which all have to be done at this time step. This is the moment that I have to do a check because I can't put a lot there anymore. So for every counter, I also have a sequence of tasks, but basically this sequence is deadline minus n long, which means I can n times, I can basically don't do a task from the sequence. And when I do a job of this sequence, basically it represents the value of the counter if I skipped already that many time steps. The counter is the number of time steps I skipped not doing a task from this sequence, which means that these counters can only increase, but cannot be more than n, because if I skip more than n time steps, the sequence is not finished. And now if I want to do a check, what I can do is I can also give what I can do is I can give some of these jobs a number of parallel jobs as well, in such a way that if this counter should not have this value at that time step, then he has all these parallel jobs. Yeah, you have to little play with the numbers, but yeah, so I give a number of parallel jobs here, and what happens is that at each time step, there is only enough machines for this large amount, and one of these blobs from a counter, but not two. And if I have, so that means that I really have to have at most one of these checks, only half of the check can fire and the other half cannot, because if both fired, then you have 2 times this large number of jobs plus this thing here, and then you have too many jobs at the time. So that's a sketch of the proof, and it's actually 1 page. So after, it's actually short. I think it's actually the proof is shorter than the proof of this 1995 paper. So you can see already by looking at it a different way, you have some extra power of proving things and even proving stronger. Yeah, okay, let's see here kind of the idea. So yeah, that was just a little bit hand-wavy proof. So let me already wrap up. I have 6 minutes left. So together with Carla and Céline, we looked at reconfiguration problems. And it's interesting that things are slightly different there. So what we have is, we have a graph. We have 2 sets of k vertices, where the size of the set is my parameter. And I want to reconfigure the first set to the second. So suppose that we look at independent set. I have an independent set of k vertices. At every time step, I can take a vertex and can move this vertex to another, change it in another one, but it still has to be an independent set. And now the question is, can I, with this type of moves, go from the first set to the second set? And so it's quite, this whole reconfiguration is an area in algorithmic graph theory in itself. But we look here at this parameterized variant where the parameter is the size of the sets. And now you can basically look at this problem in different variations. You can look at different move types, and then that's basically for several different move types the same thing holds. But you can also look at how many moves do I have? So you can say, okay, I can take as many moves as I want, or I can say, okay, the number of moves is given, and then it can be given just as another parameter of my problem, or it can be given in unary, or it can be given in binary, and the complexity depends on that. So if it's a unary, then the problem is still XNLP-complete, because basically, yeah, you can see here that you still can do this machine simulation there. If it's given in binary, it's actually complete for the class XNL. If it's a parameter, it's complete for dominating set, and W1 complete for independent set. Yes? 3 minutes? Yeah. And if it's unlimited, that's really interesting because it's XL complete, and the proof uses the old proof of Reingold that L is SL, that symmetric logarithmic space is equal to logarithmic space, or that actually solves find connectivity and undirected graphs in log space. That if you have unlimited many of moves, you can basically always revert a move. From a move, you can go also back in time. And that corresponds through the reductions to something which is called a symmetric Turing machine, which is a Turing machine where you can for every step you can do, it's also possible that the machine does a step back. So it's a kind of non-deterministic, but the only non-deterministic thing is that you can sometimes go back. You can go. So it's bounded type of non-deterministic, but actually through Reingold's result, we know that this is actually gives the same power as just a standard deterministic algorithm. And then using that, you can show that it's XL complete. And waving, but okay. So that's the last 2 minutes for my conclusions. So I hope you get, I think it's interesting that we actually really can show for some problems that are complete for a class, but also I think the XNLP idea really helps to prove things, because it's sometimes even what I said, simpler proofs, and it can strengthen some results. Then there is a very nice, interesting conjecture, and I don't know which of the Phillips 6 was free. Okay. So very good. Because they conjectured that longest common sequence has no algorithm, which runs in XP time and FPT space. But if this conjecture is true, this same conjecture holds for all XNLP-complete problems. So it's really a very, XNLP completeness actually tells us something. It tells us that it's unlikely that the XP algorithm uses little space. It's likely, it also tells us it's likely that the XP algorithm uses a lot of space by this conjecture. And then on my last slide, but I have only 20 minutes left, there are some open problems, so I'll save them to the open problem session. And thank you for your attention.